All right, welcome back. We are at Math 1920, Calculus 2. We're going to start with Chapter 5, Section 1, and start talking about natural log function. All right, so the whole point of this, all right, we want to develop and use properties of natural logs, understand the definition of what E is, and we want to find derivatives of function involving the natural log. Okay, so some of this is going to relate to logs that you've done in the past. You may have done it in math and science using log base 10. All right, we're going to get into that in a little bit in a future section here. But for the most part, it's going to be kind of some review of some log properties if you've done them before. But here's the definition of the natural log and how we use it when we apply, like, the power rule doesn't always work well for us. So it's more convenient for us to use the natural log function, all right? So this is the general power rule that we've looked back before, okay? And the issue is when n is -1 here, all right? And how it doesn't always work out well. So we're going to be able to, find some other methods for being able to solve that integral. One, okay, is the natural log function. So the definition of the natural log function is natural log of x is equal to 1 to x of 1 over t dt. All right, so natural log of x is equal to this integral that we have that's a quotient. All right, and the domain of the natural log function is the set of all positive real functions. Okay, so if we were to sketch the graph of the natural log function, so y equals natural log of x, you're able to do that in your calculator. You have the natural log key on the left-hand side of your TI calculator there when you graph this. All right, so you can hit y equals, type in natural log of x, and hit zoom 6. And put a standard 10 by 10 window. You'll get a graph roughly looking like the one that you see on the screen here, only you will not get the slope fields, all right, that we have. But what we can clearly see here is that from 0 to 1, natural log of x is negative, and then from 1 to infinity, natural log of x is positive, okay? So all these little blue ticks in here, okay, we'll talk about slope fields a little later on in a section. All right, very important in advanced calculus and things like that. We're talking about sources and sinks and that sort of thing, relative to what the slope is actually doing at those points. Okay, but if you want to sketch the graph of y equals natural x, you need to understand this basic form here. And it's always easy to start because you will always know that natural log of 1 is 0. All right, so that's kind of your premise of how you start the sketch. And then you can still, shift it left, right, up, down, stretch it, and do those sort of things. All right, so basic properties of natural logs here. The domain is from 0 to infinity, and the range is from -infinity to positive infinity. So we will not have any negative values for natural logs. Okay? The function itself is continuous, it's increasing, and it is 1 to 1. 1x, 1 out, 1y. And the graph is concave downward on its domain. Okay, so basic properties of logs. This may or may not be a review. Some of you guys should have had this in algebra, but you probably did it with log base 10, not with natural logs. This probably is your first exposure to natural logs when we talk about this. But if you look at this, it's the same properties that we use for rules of exponents for the most part. So if you're comfortable with rules of exponents, all right, it's the same thing we're going to kind of apply, right? When I talk about exponents, they have the same base and we multiply them, we add the exponents, or if we divide them and they have the same base, we subtract the exponents, so on and so forth. Okay, very similar here. But these are rules that you need to know and memorize and be able to apply, all right, when we're taking derivatives and things like that. It's really going to be to your advantage and help you solve more complicated algebraic expressions if we can solve them using natural logs. Okay, so the first one, natural log of 1 is equal to 0. We talked about that on the previous slide when we took a look at the graph. All right, and then next, the natural log of a times b. Notice ab is in parentheses here. Okay, it'll be a little bit different if it's not. But it's that quantity that's in the parentheses. We can rewrite that as the natural log of a plus the natural log of b. You're going to use that quite often along with the quotient piece and the power piece through most of this section and most of this chapter as we rewrite the logs before we take the derivative. All right, if we have natural log of a to the n, we can rewrite that. That power can come down. Notice it's on the quantity, or it's inside the natural log function. Where the parentheses are matter. If they're outside the natural log, we just use a power rule. Okay? But this becomes n natural log of a. And then lastly, we have a quotient. If we have the natural log of a divided by b, it becomes the natural log of a minus the natural log of b. It's going to be important for us to be able to apply those rules and rewrite natural logs here. So let's just do an example here. All right. If we have the natural log of 10 divided by 9, we can rewrite that as the natural log of 10 minus the natural log of 9. And this will make sense when we start getting into algebraic expressions and being able to rewrite those. Okay, next, if we have the natural log of the square root of 3x plus 2, the first step that's important, right, we know to rewrite that square root as a exponent of 1/2. So we can rewrite that as natural log of 3x plus 2 quantity to the 1/2 power. Now we can bring that 1/2 down in front when we rewrite this, all right, and we end up getting 1/2 natural log of the quantity of 3x plus 2. Okay, another example here, if we have natural log of 6x divided by 5, okay, this is using multiple properties. Okay, so when we rewrite this, we do the quotient piece first, so we get natural log of 6x minus natural log of 5. However, that natural log of 6x is product inside there, so we can do one more step when we're rewriting this example here. So this becomes the natural log of 6 plus the natural log of x, right? That product becomes a sum minus the natural log of 5. So there's how we can expand logarithmic expressions. Okay, and maybe one that gets a little bit more complicated here. If we start out and we have the natural log of the quantity of x squared plus 3 squared, all right, quantity squared, divided by x times the cube root of x squared plus 1, the first thing that we should undo is that quotient piece. So we're going to rewrite that as natural log of x squared plus 3 quantity squared minus natural log of x times the cube root of x squared plus 1. Now we've got a whole lot going on here. Okay, on the first one, we can bring that 2 down in front. Okay, and then the second one, we've got a product in there. We've got x times the cube root of x squared plus 1. So we've got to apply a product piece there. And then we've got to be able to write that cube root as x squared plus 1 to the 1/3 power. So we've got a lot that we've kind of go through here as we do this. So the next step is on the first piece, we bring that exponent down. So it becomes 2 natural log of x squared plus 3 minus, now we have that product rule, but that negative or that minus sign is going to impact each part once we do the product rule. Okay, so we have to rewrite that product as natural log of x plus natural log of x squared plus 1 to the 1/3. Okay, so we took that product, which was x times the cube root of x squared plus 1. We separated it, wrote it as a sum, and we also rewrote the cube root of x as the x squared plus 1 to the 1/3 power. Okay, do these in steps so that you don't get lost. Don't try to do too much at once when you're doing these. Okay, now we've got to move through. The first one's done. There's nothing else we can really do to it because there's no product piece or anything along those lines. So that 2 natural log of x squared plus 3, that's as simple as it gets for right now. But we can do other parts to the right-hand side. Okay, that first part is distribute the negative. All right, so it becomes minus natural log of x minus natural log of x squared plus 1 to the 1/3 power. So we've distributed the negative through. And then next, or the last step, right, we've got to bring that 1/3 down in front on the far right-hand side. And that's about as simple as it goes when we are expanding the logarithmic expressions. Okay, now what we're going to do soon is learn how to take the derivative at each piece here and simplify that down even more. But from a standpoint of being able to rewrite a logarithmic expression so that it is more manageable algebraically for us to manipulate and apply calculus to. Okay, so far we haven't done any calculus. We've just used properties of logs to learn how to expand functions. Okay, but before we start taking derivatives and things like that, we need to understand there's a base. Okay, so when you talked about logs before, and I mentioned at the beginning, right, you probably had like a log base 10. And that's the default log that's in your calculator. When you hit the log button in your calculator, the base is 10. Okay, so I'll go over a little bit more in depth in class, kind of how you rewrite this. But it's really, if we look at log base 10 of 10 equals 1, it really means 10 to the first is equal to 10. You can rewrite, exponents as logs. So the base for, regular log functions, or what we call common log functions, is 10. The base for natural log functions is e. Okay, so if you look on your calculator, you have the natural log button, and then above that, if you hit like second natural log, you have e to the x. Okay, so e is the base for natural log functions. And where e comes from, okay, it's really the area under the curve from 1 to e of 1 over t dt. It's where that area equals 1. So, right, remember that area 1e to the 1 over t dt equals 1. Well, that's the natural log of x. It equals that equation, right? That's kind of from the definition from like the first slide that we had on here. So, if I integrate from 1 to e of 1 over t dt, that equals natural log, all right, that area becomes 1. So, anytime, if I take the natural log of e, it equals 1. But what I'm saying is I'm really taking the natural log base e of e is equal to 1. And I'll rewrite that on the board a little later on so it makes sense. But know that e, okay, it goes on forever, but we use approximately 2.71, or we use the e button in the calculator. When we actually need to apply it, we just say we hit second natural log on your calculator. Gives you e to the x, but you just put in e to the first, and it gives you the value 2.711828, so on and so forth as it goes through. Okay, so if we define e, right, it's what I just showed you on the previous slide. Natural log of e is equal to 1 to e of 1 over t dt is equal to 1. It's the area under the curve from 1 to e of that integral, all right, is equal to 1. Remember that integral you're looking at, that's the definition of natural log. We just replaced x with e. Okay, so if you go back to the very first slides, that's all we've really done. Okay, and we can kind of see how e works out here on the graph. All right, so if we have e to the negative exponents, e to the negative first, e to the negative second, e to the negative third, you approximately see the values that we're getting. If we have e to the 0, it's 1. E to the first is 2.7, that's e itself, right? And then we can kind of see how it grows and how and where it lies on the graph of y equals natural log of x and how everything's related. And that's kind of why it's the base. All right? So we can see how those values work out and relate to one another. All right? But for the most part, most log functions or logarithmic functions are much easier for us to evaluate with a calculator. So on the next slide, we're going to do an example here or two, and have your calculator out and use your calculator to get these values. So in your calculator, hit the natural log button. It should be on the far left-hand side of your calculator. You're just looking for ln. Okay, natural log. I know it sounds backward. We call it natural log, and we say ln, but it comes from, SI stuff that's universal. ln means log natural, but over here we call it natural log, so that's really what we're saying. So they're interchangeable, natural log or log natural. Log natural is used more internationally. Natural log to us is here more used, domestically. But on your calculator, if you hit natural log of 2, hit enter, you should approximately get 0.69. If you hit natural log of 32, you should get roughly 3.4. Okay, so what that really means is if I take e to the 0.693 power, I'll get 2. If I take e to the 3.466 power, I'll get 32. So there's how you can kind of work backwards on it as well. If I take the natural log of 0.1, I get negative 2.303. And then if I work forward, if I take e to the power of negative 2.303, I'll get 0.1. So you can use your calculator, as a tool to go back and forth with this. Okay? So, second part is being able to apply the chain rule, all right, to the derivative. We're going to take the derivative, but for the most part, It's always going to be a chain rule unless you really just have natural log of x as we go through this. So that's why the chain rule was very important before. So if we take a look at Theorem 3.5, we're really taking the derivative of natural log functions. So like I said, the first one's very easy. If we take the derivative with respect to x of natural log of x, we should get 1 over x. If we're going to use u substitution, right? So if we have something more complex than just 1 over x, okay, we're going to take the derivative with respect to x of the natural log of u. We're just using u substitution. Becomes 1 over u times du dx. Or we can say, u prime over u, or it's really just take the derivative of the function divided by 1 over the function. Or not divided by, but just 1 over the function. Okay? So let's apply this. We're going to take the derivative with respect to x of the natural log of 2x. So, the way I see it is I'm going to take 1 over the stuff in parentheses, to simplify it down. 1 over the quantity of 2x times the derivative of 2x, which is 2, and then simplify. That's really how we treat all of these. 1 over the argument, all right, times the derivative, and then simplify. So it's going to be 1 over 2x times 2, and then we simplify that. It really just becomes 1 over x when we do this. Okay, but in terms of, u prime over u. U in this case, using u substitution, u is equal to 2x. Okay? So u is equal to 2x, du is equal to 2. Okay, so when we substitute that in, we're going to get 2 divided by 2x, all right, and that simplifies as 1 over x. We get that. Okay, let's do another example here. If we want to take the derivative with respect to x of the natural log of x squared plus 1. Well, u equals x squared plus 1, right? Du equals 2x. So it's really going to be 2x over x squared plus 1. You'll find that these end up being, fairly simple. We just have to make sure we identify u correctly. U is always going to be the quantity that's inside the parentheses of the natural log function. All right, and then you take du of that, right? Du is 2x. So it's really u prime, which is the same as du. Okay, u prime and du mean the same thing. So the derivative of u with respect to x is 2x. Okay, and then we literally substitute them in. So the derivative here is 2x over x squared plus 1. All right, now we have the derivative with respect to x of x natural log of x. That's a product rule. So you have to remember the product rule. First times the derivative of the second plus second term times the derivative of the first. Okay, so we're going to get x times the derivative of natural log of x plus natural log of x times the derivative of x. Okay, so when we break this down, it ends up being x times 1 over x plus natural log of x times 1, right? The derivative of x is just 1. So when we simplify this down, we get x over x, which equals 1, plus natural log of x times 1 is natural log of x, so we end up with 1 plus natural log of x. So you do have to recognize the product rule, to apply it there. Okay, and let's take a look at this one. Notice we're going to take the derivative of natural log of x quantity cubed. That's just the power rule, but we have a chain rule with it, right? So that 3 has to come down in front, and then we have to multiply by the derivative of the inside. We'll get a little bit more in depth in class, all right? But it's really important that we understand the chain rule function here. It's because the cubed is on the entire natural log of x function. If it was just on the x piece, okay, we could bring that 3 in front and then just take it times the natural log of x, but it's not. So we have to use the power rule and the chain rule kind of combined, right? So we bring the 3 in front and we subtract the power, so it becomes 3 natural log of x squared times the derivative of the inside stuff, which is just times the derivative of natural log of x. Okay, so when we do that, we're going to get 3 times the natural log of x squared times the derivative of natural log of x, which is just 1 over x. Okay, so that would be kind of our final solution. You'd have 3 natural log of x quantity squared all over x when you do that. Okay, now sometimes it's easier for us to use logarithms in differentiating non-logarithmic functions as well. We call that logarithmic differentiation. Notice, what does that really mean, all that verbiage we just went through? Notice this isn't a natural log function yet. It's a y equals, and it's a quotient rule. However, we can take the natural log of both sides of this function and apply rules of natural log. Because, undoing or taking the derivative of this is a really painstaking quotient rule, right? If we were to sit here and go low d high minus high d low all over low low, all right, it's going to be a lot of work for us to work through all that one. Whereas if we apply logarithmic differentiation here, all right, makes it a little bit easier because I can rewrite this. That's the whole point. We want to do logarithmic differentiation so that we can rewrite these functions so that they are simpler functions for us to work. So, that being said, it goes back to the old cliche algebra piece. What you do to one side of the equation, you do to the other. So, I can take the natural log of both sides of this equation here. Okay? So, when I do that, the very bottom here, I can take the natural log of both sides of the equation. So on the left-hand side, I'm going to get the natural log of y, and I'm going to say that equals the natural log of that entire function there, x minus 2 squared divided by square root of x squared plus 1. That aids me in rewriting some things before I take the derivative. I can rewrite that right-hand side now, okay, using the properties of logs. I'm going to step back a slide, right? I have x minus 2 squared all over square root of x squared plus 1, right? I can see that's a quotient, so I can do that and rewrite it as a difference, okay? And then the powers can come down. So I can rewrite that using the properties of log. So I have natural log of y equals 2 times natural log of x minus 2 minus 1/2 natural log of x squared plus 1. So we use the log properties there. We used an exponent one and we used the quotient. That's where the subtraction piece came into play. Now this is way easier for us to take the derivative of. So now we take the derivative of the left side and the right side when we do this. The derivative of the left side becomes y prime over y, right? Because u equals y there and it's u prime over u. We had to do it with respect to y. And it's important that you do that because it's y prime over y. That y is going to come into play here in a little bit. Then we take the derivative of the log functions, which is just going to be 1 over the function, or 1 over that quantity, times the derivative of that quantity. So it's 2 times 1 over x minus 2 for that first part. And then the second one, it's going to be 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. So that's where that came into play. All right? Then we can simplify some things down, all right, algebraically. Okay, so I'm only working with the right-hand side right now. If we simplify it down, find the common denominator, and distribute things through. I'll go in more depth on this example on the board in class and show you the missing steps to the algebra here. All right, but this is still equal to y prime over y. Okay, so it's very important there, and we're going to solve for y prime. So all we did in that step here where I said simplify is we found the common denominator and then manipulated everything in the top based on like terms. Okay, you should be able to do that, but like I said, I'll go over in class. Next, we're going to solve for y prime because we're differentiating, right? So that means I have to multiply both sides of the equation by y. Now, y is what we originally started with, so that comes back into play here. Y is the original function, so I'm going to replace the letter y with the original function, which is x minus 2 quantity squared over the square root of x squared plus 1. Okay, so I can simplify. Notice now I have an x minus 2 in the numerator and an x minus 2 in the denominator. One of those will cancel in the numerator, and the one in the denominator will cancel. And then in the denominator, I have the square root of x plus 1. I can rewrite that as the square root. I'm going to rewrite the square root with a 1/2 power, so it becomes x squared plus 1 to the 1/2. And then I have x squared plus 1 to the 1. When I multiply those, I add the exponents. Okay? So when I do that, in the denominator, I get x squared plus 1 to the 3/2. That comes from adding the exponent of 1/2 plus 1. Gives me 3/2. All right? And then the x minus 2 that's in the numerator that's remaining, it's because one of the ones in the numerator canceled with one of the ones in the denominator. Okay, and that's really how we simplify those down. And like I said, I'll get into the depths of that with the algebra piece in class a little bit more. Okay, next, we want to be able to find the derivative involving the absolute value function. So, this is theorem 4.4, or 5.4. If u is differentiable function of x such that u is not equal to 0, then we can say the derivative of the natural log of u is equal to u prime over u. So nothing changes here, okay? Because we're really only talking about the positive values here when we do this anyways, okay? Since we're dealing with natural log. So it works out really well. So let's do an example here. We want to find the derivative of the natural log of cosine of x. Okay, so we're going to apply the same thing that we've been doing with the derivative of natural log. So it's going to be 1 over cosine times the derivative of cosine, which is minus sine. Okay, so then we end up with negative sine over cosine, which ends up with being tangent. Okay, so u in this case is cosine if we're doing the u substitution. If we let u equal cosine, du equals negative sine of x. Okay, so you're going to end up with negative sine over cosine, right, when we do this, and then negative sine over cosine, or negative sine of x over cosine of x, right, just gives us negative tangent of x. So there's not a big deal when we have to do the absolute value function. It works out just like if we're doing the normal or regular function when we're taking the derivative of a natural log. All right, well, that's the end of section 5.1. You guys can ask me any questions when you get to class, or email me with any questions if you got anything else, guys. Have a great day. I'll see you in class.